Okay, so thank you very much for inviting me to talk about our current EU-funded project for the design study of the Atacama Large Aperture Submillimeter Telescope, AtLAST. This is a project involving 5 different institutes in Europe. It's coordinated by us in Oslo, but there are many people working on it. And this list is non-complete. It's key people that are, leading big chunks of the project. And in today's talk, I will give a broad overview of the project, but also include some preliminary results from the first year of work. Okay, so in a very short summary of the goals of this design study. So what's a design study? It's a feasibility study. Okay, we need to build a new observatory, and we want to make a comprehensive design study considering all possible aspects and challenges of building a new facility. And what I want to say is that this is a very ambitious telescope. I will give more details later, but the technical requirements for these telescopes are uniquely driven by science, okay? So it's not an incremental project, it's a project where we asked ourselves, what's the science that we cannot do with current facilities or even current upgrades to current or future facilities? And from those answers, we define the characteristics of this telescope that we want to build. What we want is a 50-meter diameter single dish telescope operating in the submillimeter and millimeter range with a very high throughput, higher than Zika prime, we will see later, and a field of view of 2 degrees diameter. The telescope will need to observe high frequencies as well as lower frequencies, so it will need to be located in a high dry site in the Atacama Desert. We are exploring locations on the China Tour Plateau, which I'm sure many of you know. It also hosts ALMA, Apex, Simon's Observatory, Zika Prime, and other famous projects. AtLAST is an international partnership that is open to collaborations. For example, some of you may know of a sort of parallel effort from the Japanese community called LST, and I'm happy to say that we will eventually merge, so there will be only one AtLAST/LST telescope. But we also know that several teams in the US, Canada, Australia will be interested in participating. But what we want to do is the facility where Europe has really a central role. We want a facility telescope with open time for PIs to apply, so not the service telescope only, and the flexibility to host multiple instruments. The current designs include 6 spaces, 6 science instruments. And most importantly, this is the first that we are aware of, the first design study of a new astronomical facility that plans to make this facility fully powered by renewable energy. And this is a part of the study that is, as you may imagine, is not led by astronomers, but is led by engineers here at the University of Oslo. Okay, so why do we need a new large submillimeter single dish? We have many submillimeter single dishes already in the world. These slides show some of them, and some of them are also high aperture ones. Well, the reason is that none of them can actually can remain competitive in the late 2020s. And none of them can enable us to perform the science that we want to do. So the main reason is that most of them have a small aperture, and this implies not just a small collecting area, and but also low spatial resolution, and the two combined together gives us what we call the confusion noise, which basically means that you're including multiple sources in your beam, and so this you cannot identify or study the individual sources, and this translates into effectively into a sensitivity floor of your survey, meaning that you're sampling only the tip of the iceberg of of the population that you're studying. Could be galaxies, star forming regions, protostellar cores, etc. And this cannot be mitigated by, having multiple dishes working together. And because we need a resolution, we need a large aperture. The current large aperture facilities like the 50-meter LMT, the 130-meter, the Nobeyama, cannot observe at high frequencies, okay, because of the design, their surface accuracy, but especially because of the atmospheric transmission in the site where they're placed. And instead, there is a very high sensitivity pressure to probe high frequencies higher than 400 gigahertz. You will see later. And finally, all of these telescopes, apart from the cosmology telescopes, which don't deliver the resolution, have a small field of view, meaning that they have very low mapping speed, and several science cases that we're interested in are requesting to map very large fields, several hundreds or even thousands of square degrees. Okay, so when we submitted our proposal to the EU, we had in mind 4 main, very ambitious science goals that we want to perform with AtLAST, okay? And then now we're learning that there is actually even more transformational science that we can do, but let me go through these main 4. So the first one is to perform the deepest, highest resolution, most complete survey of molecular gas and dust in our own galaxy. So this map here, you probably know very well. It's the Planck vision of the galactic plane, and it shows both the dust and the molecular line emission. And the plot on the right shows a map obtained with ALMA combined with the RM30-meter of a portion of the Orion giant molecular cloud, which shows this typical filamentary structure of the ISM. Okay. AtLAST will give us the comprehensive environment that we have from Planck, together at the same time with the details that you can see in this map on the left. So this is on the right. So this is really transformational because you can link the properties, the chemistry, the physical properties of the ISM down to resolution of below parsecs, okay, for objects at the galactic center, and you can link all of this information to the larger scale environments. So you can study for the first time star formation as a function of, environment, magnetic fields, turbulence, gravity, but also place constraints on the IMF, study the phase transition between atomic and molecular gas, etc. This is really transformational. The second goal we had in mind was to perform a sub-millimeter version of the SDSS extragalactic survey, both in imaging and in spectroscopy. So we know, about half of the radiation emitted by stars is absorbed by dust and re-emitted thermally in the far infrared band. But what we're very lucky in the sub-millimeter wavelengths, because at high redshift, by redshifting the light to longer wavelengths, what happens is that it's shown in this plot here. This is the dust spectral energy distribution of a star-forming galaxy for a redshift 1 down to redshift 10, the same object, okay, just redshifted. And this band here, orange, shows the sub-millimeter range. So you can see that in these wavelengths, you basically, at any redshift, you basically see the same intensity of the dust emission. And this is because at higher redshift, the sub-millimeter bands are sampling closer and closer to the peak of the SCD. And this is called the negative K correction. And this enables us basically to counteract the cosmological dimming. So we see with the same brightness galaxies from redshift 2 to redshift 10, okay? And this was exploited in past sub-millimeter surveys with small aperture telescopes. However, these surveys discovered a new class of galaxies that were initially called sub-millimeter galaxies. But these are, again, tip of the iceberg of the galaxy population. These are not even galaxies, these are protoclusters, many of them. So we really need to go down to the typical star-forming galaxy in the universe, and AtLAST can do that in just a few years, in multiple bands and in line emission. And so this will, of course, open up, the complete census of star-forming galaxies, out to the reionization network and help us investigate galaxy evolution and related with the environment and large-scale structure. Then the third main science goal that I'm particularly interested in is the possibility with AtLAST to detect something that is completely invisible with current facilities. And these are hidden, extended low surface brightness components of the circumgalactic medium. So the circumgalactic medium is basically the gas that is not as bright as the interstellar medium of galaxies, so it's not high surface brightness gas, but this gas that we believe is still hosted within the dark matter halo of galaxies. And we need this gas in order to close the baryon budget of galaxies. And up until a few years ago, we thought that most of this gas would be warm, hot, okay? But new results are showing that actually a very large fraction of this gas may be in a cold molecular phase, which, however, we cannot detect in any possible way. And this little exercise shows why. So this is a simulated CO emission from the ISM and CGM of a local star-forming galaxy. So this is the input of this little simulation. And then we asked ourselves, what would ALMA or the ACA, which is the compact array of ALMA, see after 10 hours of observation? This is a massive galaxy, okay? It's just a very nearby galaxy. So this is what they see nothing. And this is because ALMA has a very small field of view. And on top of that, it is an interferometer, so it's filtering out everything that is extended at low surface brightness. So basically with ALMA, you only detect the point sources because it's a very, very sensitive to point source emission, okay? With ACA, you don't detect anything. And this is also because, again, you need to have, more than 500 pointings with ALMA to cover this region, which is only, basically not even the whole dark matter halo of this galaxy. And with the 50-meter single dish equipped with a single ALMA detector, so this is a much worse than what AtLAST will do, which will have multiple detectors, you can recover all of these emissions. So this exercise shows that any diffuse extended molecular CGM reservoir around the local galaxy will remain completely undetected with any current facility, especially a low redshift. And finally, I think for this audience, it's particularly interesting the perspective of detecting and resolving both the thermal and the kinetic Sunyaev-Zeldovich effect down to individual massive galaxy scales, okay? So this is a spectrum of the signal from the SZ effect, the thermal and the kinetic one, as plotted against the atmospheric transmission at the China Plateau, where we are considering to build AtLAST. And you can see that in order to disentangle the two components, okay, so the SZ effects is basically this secondary anisotropy of the CMB that is caused by the fact that the CMB photons are inverse Compton scattered by electrons in a hot medium, okay? So every time these CMB photons have to pass through a hot medium, their spectrum changes, and it changes in a unique way that is independent from redshift. And if we understand and map this change, we can understand how much gas there is there through the thermal SZ effect, but also we can study the peculiar velocity of this gas through the kinetic SZ effect. But in order to perform a proper component separation, we need to sample from 30 down to 50 gigahertz in frequencies, okay? We need to do it with a high resolution because we need to also to sample the emission from the dust and the synchrotron, that is, contaminating our SZ effect. And this is shows an example of a simulation with a 10 arc-second resolution, which is more or less what AtLAST will deliver. And you can detect the thermal and the kinetic SZ and also identify all these small components, which are actually groups and clusters of galaxies that with a 6-meter class telescope you smear out in your beam. Okay, so a little bit about the project implementation. The project, the design study lasted 3.5 years, started about a little bit more than a year ago. The total cost of the design study is 3.5 million euros. And there are 5 partners, as I said. So this is a very comprehensive study. There are 6 work packages, so 6 main activities. The first one is the general management, which is also in charge of delivering a plan for the governance structure of the AtLAST Observatory, and is led by us. Then we have the telescope design, which I will go a little bit more in detail about, the site selection part of the work, the operation study, so how we operate the telescope, the environmental sustainability study, and the science case study. So the part of the project that is the most expensive in terms of personnel months and funding is the telescope design. Okay, this is supervised by Tony Roskovsky at ESO, and it's carried out by our industry partner, which is the OHB Digital Connect company in Mainz, which some of you may know as MTM, MT Mechatronic, but they were merged. So they're doing a great job. They have decades experience in building larger dishes. We presented them with a really big challenge. So this table shows the goal requirements of AtLAST that we put in the proposal, okay? The minimum requirement and the goal requirement on the right. I just go through some of them. So the wavelength range is the same as ALMA, okay? The aperture goal is 50 meters, field of view 2 degrees in diameter. Surface accuracy 20 micron. This is comparable to the ALMA antennas, which are 12 meter diameter. The only difference is that here we have to reach this halfway front error on a dish of 50 meters. This is very, very challenging, okay? So we need active optics because wind, gravity, and thermal influences can severely impact the surface accuracy. We want to perform solar observations. We want to cover this elevation range, and we want a very high pointing accuracy, very high scanning speed, 3 degrees per second, and we want a very high sight above 5,000 meters. So all the black V that you see here are those requirements that have been accepted and implemented in the current design, okay? So no problems on these ones. The ones that are in white are possible with the current design, but more expensive and challenging, okay? In particular for the, as I said, surface accuracy, we can achieve that, but it's gonna be probably expensive. Solar observation, we can do that, but again, we need a particular coating on the surface, which may increase the cost. Pointing accuracy is intended as a tracking accuracy and astronomical pointing. The blind mechanical pointing is 2.5 degrees, the one that OHB will deliver. But this is not a problem because we are never going to be only with one beam on the sky. We're always going to have multiple beams. So as long as the source is in the field of view, we can work with the astronomical pointing models as we do with AtLAST, with the Apex, and we can go down to a very high pointing accuracy. Okay, so there's going to be no enclosure, so we need a surface tower. So just to show you how AtLAST compares with other current or planned single dish telescopes, I think these plots are very useful. These plots include only single dish telescopes that can observe at least up to 270 gigahertz. Most of the ones that can observe up to 270 gigahertz cannot observe higher frequencies, but we needed to put a cut, otherwise there wouldn't be any data points in this plot. So this is primary mirror diameter on the left and the corresponding angular resolution at 1.1 millimeter. You can see AtLAST is up here. So it's the telescope that delivers the highest spatial resolution, okay? The LMT is the Mexican 50-meter telescope, but the LMT can observe much lower frequency, cannot observe higher frequency. Nominally, it can do 270 gigahertz, but I have never seen this data. So basically, it's not there yet quite. Central plot shows the field of view for different facilities, and you can see AtLAST is just a little bit smaller than SICA Prime. But if you compare AtLAST with any other telescope that can do galaxies, This is, orders of magnitude better. And finally, the throughput, which is the product of the aperture by the field of view, AtLAST has a throughput that is even higher than SICAP Prime and Simon's Observatory, okay? So this gives you really the mapping speed and the sensitivity in a wide surface. Optics, I don't know if this audience is interested in how we're gonna reach this 2 degrees field of view on a 50-meter dish. This is a question that I get very often, but the answer to this question is that, we're gonna use this optical design, which is published on our website. Is a memo wrote by Richard Hills. And basically we're gonna have a classical Ritchie-Chrétien arrangement with 2 imaging mirrors and 1 and 2. And 2 is going to be huge. It's going to be 12 meters, okay? So 1 ALMA antenna. And then we're going to have a flat tertiary mirror, which has no imaging features, but it basically just folds the beam into the elevation axis. And you can see that the focal plane has a very large sides and a significant curvature. So this needs to be taken into consideration when building instruments for AtLAST, but it is possible to overcome this challenge. We already have some ideas. And the diffraction limit of field of view delivered by the telescope is, of course, not the full field of view, but it can be improved by shaping entry, okay? And it can be improved also through the instruments optics. Maybe I'll skip this slide, but I'm not allowed to share the design yet. The CAD model, it will be delivered at the end of the project. But we needed to basically change completely the design of typical radial submillimeter telescopes. The typical National Cassegrain design does not work, because we have large optics and we need a large cabin for the instruments. So our new design is inspired by 30-meter plus optical telescopes, actually. And in the end, it allows for 6 science instruments, 2 with a 2 degrees field of view and 4 with a 1 degree field of view. Okay, so work package 3 is working on finding the best site for AtLAST. It's led by ESO. We are studying 2 locations on the China Tour Plateau, one inside the ALMA ESO concession and one outside it, which is shown in this blue contours. This is the Atacama Astronomy Park, where the cosmology experiments are also placed. The reason why we want to be on China Tour is to minimize the impact on the environment, because we can use existing infrastructure, we can use Apex as a pathfinder, and we have the very good weather condition. We have lots of data, historical data, which we are analyzing also to study climate change and how this will affect the quality of the atmosphere on China. But we will also take our own data. We need to measure the wind profile across a 50-meter height, because there is not a 50-meter telescope on that plateau yet. And there is also some politics involved for the legal aspects of this work. We're gonna also work on defining the operations plan for the observatory. Here we're also capitalizing on the ESO expertise and the lessons learned by operating telescopes on Paraná, La Silla, and China Tour. In this part of the work, we will define, for example, plans for how much time is given to PI science, how much time to survey, whether there is going to be some GTO time for teams developing instrumentation, etc., etc. The environmental sustainability part of the work is led by the Department of Technology Systems here at the University of Oslo. They have an expertise in energy storage, in batteries and hydrogen. And it turns out that powering a telescope with solar energy is not that easy, because you need to have a 24 hours power, okay? So previous projects have considered, hotel or, houses where in the night you don't need energy. But for a telescope like this, you need to keep the instruments continuously on, and you need to power operations for 24 hours. And on top of that, we know by experience that on Chinator, the best weather conditions, you have them just after a snowstorm. So you need to store energy to be ready to exploit this perfect weather after, maybe a few days of snow, during which you haven't had access to solar energy. So a lot of work will be on defining a plan to store energy in an efficient way to power the telescope. But there are many, many challenges here. Anyway, the reason why we want to do this are obvious, but there are also some less obvious reasons. Is that, apart from being climate positive, a green telescope can also be cost effective on the long run. Okay, we see now with the energy crisis that we all know about. Okay, and then the science work package has many, many different aspects. For this audience, I think what is most interesting is we are of course using the expertise in the wide community, even outside the AtLAST consortium, to develop what would be the white book of AtLAST, the main science drivers. And of course, we already have some expertise within the consortium, but what we are doing is to gather info from the community. And in the first phase of this community survey, we received so-called use cases for AtLAST, about 30 of them, from more than 100 external contributors from all over the world. And we grouped them in 4 broad science themes: solar system, Milky Way, nearby universe, distant universe, which also includes cosmology. And the results of this community survey are published on our website. And these are the starting points to develop the science cases, okay? So some of the key results are that in terms of spectroscopy, there is a high request of what are the ALMA bands 6 to 8 frequencies. Okay, so we knew that already, but this is very, very clear from this survey. So this is the project as a function of the frequency band divided by instrument that is required: heterodyne, MOS, multi-object spectrograph, or field eye type of instrument. And you can see band 6 to 8 are really the most requested ones. Band 6, you see CO221 at redshift 0, for example. Band 8, you can detect atomic carbon at redshift 0, etc. For wideband imaging, so continuum observations, there is a strong pressure to maximize the number of pixels or beams on the field of view. Some of these use cases, including one of mine, request to map areas that are, more than 1,000 square degrees on the sky. So this is really, really interesting and ambitious science. Here at the University of Oslo, we are also, as part of the science work package, we are producing some predictions for what AtLAST will see in galaxies. And this is not trivial, because there is currently no hydrodynamical simulations that can resolve and track the formation of cold gas in a cosmological, box. So we need to use this very, very high resolution simulation, the one we are using as a resolution of 900 solar masses, which is very high, but still not enough to follow up from, ab initio, the formation of molecular gases. So on top of that, we need to model the emission lines that AtLAST will detect. And the results are still, work in progress. A PhD student here at Oslo is working on that. But there are very, very promising results. So as you can see, this is a map of the carbon plus emission from a galaxy volume at redshift 6. And you can see carbon plus comes both from the ISM of these galaxies, this is a merger, but also from some expanded CGM, IgM gas. We can actually detect both outflows and inflows, but everything is very blended and everything is very difficult to disentangle. And also she's testing different models to model the line emission. And it turns out that the results are very, very sensible to model parameters, okay? So there is a very high risk in simulations and current works of confirmation bias. Basically, current simulation tweaking their models to fit the current observational constraints, which may be wrong because, as I said, they may be missing a significant extended components around galaxies. Okay, so I will skip this and go to the last slide where, I just, there is a website which we try to keep updated of whether, all the results eventually will be made public at the end of the project. But as you understand, when they're still preliminary, we are not allowed to share them. But everything we can share is on the website, including some outreach style articles, especially the last one was a report of our trip to China a few months ago. And there is a form that you can use to contact us and tell us if you want to collaborate. And especially for this community, we welcome collaboration with groups developing submillimeter instrumentations and the contribution to the science case. And thank you.